Alright, so in this video we're going to be looking at a lot of things that most of you have probably already seen before. We're just going to try to expand upon it, of course make it more difficult as we always do, and then hopefully make it a little bit more useful in terms of things that we've been doing. It's also very important that we thoroughly understand all of this, because just like most things in mathematics, we're going to build upon it throughout the course. So first, starting off with some definitions we need to get comfortable with. A sequence is going to be an ordered list of numbers, A1, A2, A3, bunch of things all the way up to AN, maybe on forever, right? So like if I take the numbers 1, 2, 3, 4, 5, going on forever, that's a sequence of numbers. We often denote it by this curly bracket AN, and then we put like n equals 1 to infinity. We could do something like n equals 0 to infinity, n equals 3 to infinity. It doesn't matter where we start. But if we don't write where we start, it is just assumed, like in this case, that we are starting with n equals 1. Each number in our sequence is going to be called a term. So for example, if we take this sequence, AN, this infinite sequence, that starts with n equals 1, then the third term would be given by A3. The successor of a term is the term that comes directly after it. That is, so say we have some sequence, right? A1, A2, A3, A4, going on forever. The successor of A3 is A4, because A4 comes directly after it. So let's look at example 1. We want to find the first three terms of this sequence. And we're told that we start off with n equals 2. So I'll find A2. The way I find that is I take this, I take this formula right here, and I just plug in n equals 2. So we'll get 2 plus 1 over negative 2 minus 2. And that'll give us 3 over negative 4. A3 would give us 3 plus 1, which is 4, over negative 3 minus 2, which is negative 5. And then A4 would be the third term of our sequence. It's going to be 4 plus 1, which is 5, over negative 4 minus 2, which is negative 6. Now for example 2, we have maybe what seems to be a bit more complicated formula, and we want to find the first four terms of this sequence. So we're not told what it starts with, so we assume it starts with A1. So A1 is going to be negative 1 to the 1 times 1 cubed. So this would be negative 1 times 1, which will give us negative 1. A2 would be negative 1 squared, right? Negative 1 to the 2, so that'll be a positive 1, times 2 cubed, so times 8. So that'll give us 8. A3 would be negative 1 cubed, so that'll be negative 1, times 3 cubed, which is 27. So that'll give us negative 27. And then A4 would be negative 1 to the 4th, so that's 1, times 4 cubed, which is 64, so that'll give us positive 64. Notice here, our terms alternate between negative, positive, negative, positive. When we have something that alternates like this, we call it an alternating sequence, right? So an alternating sequence is whenever our terms alternate back and forth between positive and negative. In example 3, we're given a different type of sequence. We want to find the first four terms. Well, the first one, A1, is given to us. So we'll have A1 equals 6. Then to find A2, we use this formula right here. So notice that A2 is going to be equal to, this is the same thing as saying A1 plus 1. So this will be our n value. So this is going to be A, so this is our n value, so we should have A sub 1 over 1. So this is 6 over 1, which is 6. Now let's say I want to find A3. Well, that would be A2 plus 1. So this is going to be our n value. And so this is going to be a2 over 2, which is 6 over 2, which gives us 3. And then finally, we'll have a4. That's the same thing as a3 plus 1. So 3 is our n value. So I should have a3 over 3. So that'll be 3 over 1, which gives us, 3 over 3, which gives us 1. Right? So notice here, this 6 gave us this 6. Gave us, this 6 right here. That's our a1. And then this 6 gave us our a2. And this 3 gave us our a3. Whenever we're building off of our previous terms, this is going to be called a recursive sequence. And you can identify a recursive sequence by, we're given something by a sub n plus 1, and in order to create that term, we use the predecessor a sub n. Okay. So now let's look at example 4. Example 4 gives us another recursive sequence, and we want to find the first 4 terms. So a sub 1 would be 1, that was given to us. A sub 2 would be equal to a sub 1 plus 1. So it's going to be 2 times a sub 1 minus 3, which will give me 2 times 1 minus 3, which is negative 1. Then a sub 3, that's the same thing as a sub 2 plus 1, so our n value is 2. So we'll get 2 times a sub 2 minus 3. So that'll be 2 times negative 1 minus 3, which gives me negative 5. And then finally, a sub 4, that'll give me a sub 3 plus 1. So 3 will be our n value, which is going to be equal to 2 times a sub 3 minus 3. So this will be 2 times negative 5 minus 3. So this will give us negative 13. Okay, now that we've looked how to get the terms given a sequence formula, I want to look at, okay, well, if we're given terms, how do we go from those terms to the sequence formula? So the first thing I want to notice is that this is an alternating sequence. We go from positive to negative to negative. Instantly, whenever I see that, I know that my formula is going to need to have a negative 1 to the n or negative 1 to the n plus 1. To decide which one I need, I can look at, okay, well, this is the third term right here, a sub 3, and it's positive. Notice if I calculate negative 1 to the third, that'll give me a negative number. But if I do negative 1 to the 3 plus 1, that will give me a positive number. So that's what tells me I need to have negative 1 to the n plus 1. Okay. So we're going to have negative 1 to the n plus 1, and now I need to figure out the rest of it. To figure out the rest of it, I'm going to omit these negative signs and just look at our sequence. So the numerators, the numerators give us a sequence of 1, 2, 3, 4, and so on. And so that tells me that if this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, then if I want the nth term, a sub n, it's just going to be n. So then over here, I need n divided by whatever formula we get for the denominator. For the denominators, we're given 4, 9, 16, 25. So this is a sub 1, a sub 2, a sub 3, a sub 4. Well, I noticed that this sequence is the same thing as saying 2 squared, 3 squared, 4 squared, 5 squared. And so this looks like 1 plus 1 squared, 2 plus 1 squared, 3 plus 1 squared, and so on. So our bottom is going to be n plus 1 squared. And so then this will give us our formula for the given sequence. Now let's look at example 6. To make this a little bit more friendly, we're going to think about this starting number, 1. Instead of calling it 1, I'm going to call it 1 over 1. The reason I'm going to do that is so that we can look at this in terms of numerators and denominators. So my numerators, these are all 1. So that tells me that in my a sub n formula, I should have 1 divided by something. We don't know what that something is yet. Then for the denominators, I have 1, 2, 6, 24, 120. This is going to be a pattern that we need to get very used to. So this first term, this looks like 1. The second term looks like 2 times 1. The third term looks like 3 times 2 times 1. The fourth term, that looks like 4 times 3 times 2 times 1. And so now we should notice this as n factorial on the bottom. So this will be our formula for this sequence. For example 7, there is absolutely no reason this should be bolded, except for the fact that it just is. But I'm going to do this one and then leave example 8 as a practice problem. So here we've got, let's see what we have. We have 3, which is the same thing as, let's see, how do we want to rewrite this? Notice that if I wanted to break this up into numerators and denominators, this would be 3 over 1. This would be 2 over 1. So my denominators would start off as 1, 1, 3, 9, 27. Well, it doesn't make a whole lot of sense to me. So instead of looking at this as numerators and denominators, I just want to look at this sequence and think, what do I have to do to one number to get to the next number? This is often another strategy of figuring out what our sequence is going to be. Well, if I want to go from 3 to 2, then I need to multiply by 2/3. One way of figuring this out is like saying, okay, I have 3, I'm going to multiply it by something, and I want it to be equal to 2. So if I divide by 3 on both sides, I'd get x equals 2/3. Okay. Now, to go from 2 to 4/3, again, I could just multiply by 2/3. Here, to go from 4/3 to 8/9, it's the same thing, multiply by 2/3. And then the same thing once more. So here, when you see something like this, one way to do this is that we start with the first number, so we have a sub n equals 3. And then we multiply by 2/3 to some power. Well, if I want a sub 1 to be equal to 3, then I need to make this n minus 1 instead of n. The reason is that when I plug in n equals 1, we'll get 2/3 to the 0. So it's almost kind of like we just take away this portion of our formula. All right, and then we're leaving example 8 as a practice problem. Now let's look at the definition of the limit of a sequence. Whenever you see something that looks like this, limit subscript n to the infinity, that's the same thing as writing it like this. And basically what it means is as we go on forever in our sequence, what number are our terms approaching? Right, so if I give you some sequence like 1, 2, 3, 4, 5, then it's safe to say that if we go on forever, we're approaching infinity. Okay, so now let's see, how do we evaluate something like that? Well, if I am given this sequence, a sub n, and its formula, then if I want to take the limit as n goes to infinity, all I'm doing is calculating the limit as n goes to infinity, and then just plug in the formula for a sub n. So this would be limit n goes to infinity of the square root of 4n plus 3 over 7n plus 6. Now is a great time for us to recall that when we have the limit of a square root function, since the square root function is going to be continuous, given that we don't have any negatives in here, we can move our limit inside the square root. So this becomes the square root of limit as n goes to infinity of 4n plus 3 over 7n plus 6. Now we can utilize L'Hopital's rule when we're just looking at the limit of this fraction right here. L'Hopital's rule says that since we have a continuous function right here, and we have infinity over infinity, or plus or minus infinity over plus or minus infinity, I can take the derivative of the top and of the bottom to get our answer. So if I take the derivative of the top, that'll give me just 4, and taking the derivative of the bottom would give me 7. So then the limit of this sequence is going to be the square root of 4 over 7. Alright, whenever I perform L'Hopital's rule, I'm going to leave a little LH here, as you should, to indicate that's what you did to move between answers. Now let's look at example 10. So here, again, if we want the limit as n goes to infinity, we just take our limit of the formula for this secant, or for this sequence. So it's going to be cosine inverse negative n plus 1 over 2n plus 3. Again, we have a continuous function here, so I can move my limit inside the function. So this is going to be cosine inverse of limit as n goes to infinity of negative n plus 1 over 2n plus 3. And now we have another L'Hopital's rule, or as I like to say, L'Hospital, meaning that when your limit is sick, you take it to the hospital, that way L can fix it. So this is going to be cosine inverse of negative 1/2. And refreshing ourselves on how arc cosine or cosine inverse works, we're looking at the domain of the function going from 0 to pi. And so I want to know, okay, well, what value between 0 and pi will make cosine of x equal to negative 1/2? And that value we're looking for is 2 pi over 3. Because cosine of 2 pi over 3 gives us negative 1/2. So I'm going to leave that right here. Now, for example 11, this one's a little bit more complicated. The trick here, so we have limit as n goes to infinity of... So the first thing I'm going to do is factor out a 1/3 from this formula we were given. So I get ln of 3n plus 1 minus ln of 4n. The next thing I'm going to do is use our log rules to rewrite this. So this is going to be the limit as n goes to infinity. Also, before I do that, I want to note that when we have a constant being multiplied by everything inside our limit, we can bring that constant outside our limit. So this is 1/3 times the limit as n goes to infinity Now I use my natural log rules to rewrite this as 3n plus 1 over 4n. Just like before, we're going to utilize the fact that we have a continuous function. So I'm going to move this limit inside our natural log. Then we can take our limit to the hospital, use L'Hospital's rule. And so we'll take derivative of top and bottom. That'll give me 3 over 4. So then our answer is going to be 1/3 times ln of 3/4. Now for example 12. So here we have the limit as n goes to infinity of n divided by ln of n squared. Okay, so my first step here is just going to be, so I can't move the limit just straight inside the ln because we're going to get an infinity, and we'll take natural log of infinity. So it looks like we're going to get like infinity over infinity squared. So it doesn't really tell us much because we don't know much about different sizes of infinity right now. However, what I can do is I can just straight off the bat do L'Hopital's rule. So taking the derivative of the top, we'd get 1. The derivative of the bottom, we use chain rule to get that this is 2 ln of n times the derivative of ln of n, which is 1 over n. And so this will give me limit as n goes to infinity of n over 2 ln of n. So I'm going to take this 1/2 and pull it outside of our limit. And that will give me n over ln of n. And now I'm going to use L'Hopital's rule once more. So this will give me 1/2 times the limit as n goes to infinity of 1 over 1 over n. And this will give me 1/2 times the limit as n goes to infinity of n. And so now I'll have 1/2 times infinity, which is infinity. In this case, we say that the sequence diverges. In all of our other cases so far, we can say that our sequence was converging to some number. But in this case, we say our sequence diverges. Now let's look at example 13. So for example 13, I'm going to leave this as a practice problem. And the key here is to, just like ln, e, the exponential function, is a continuous function. So we can move that limit inside e. So we'll be taking e to the limit as n goes to infinity of that exponent. And we can use L'Hopital's rule there. Alright. For example 14, this one's a little bit more tricky. So we should have the limit as n goes to infinity of n over n factorial. So notice this. If I have 5 over 5 factorial, that's like saying 5 over 5 times 4 times 3 times 2 times 1. So we cross out these 5's, and we're just left with 1 over 4 factorial. Another way of thinking about this is that I'm rewriting 5 factorial as 5 times 4 factorial. That way I can cancel out 5's. So what I'm going to do here is I'm going to write this as limit as n goes to infinity of n over n times n minus 1 factorial. So then my n's will cancel out, and I'll be left with the limit as n goes to infinity of 1 over n minus 1 factorial. So as n goes to infinity, this denominator is going to get infinitely large, which means that we're going to be headed towards 0. Now let's look at example 15. Example 15, if I graph it out, is going to look something like this. So my first point, this is not example 15. So my first point's at 0, and then 2, and then 0, and then 2, and then 0, and then 2. This is an example of what we call a oscillating function. Whenever we have an oscillating function, right, it's bouncing back and forth between two numbers, this is always going to diverge. So we can say since our sequence oscillates, it must diverge. Now let's look at example 16. Example 16, there's two different ways to do this. One way is to, so this is going to be the limit as n goes to infinity of cosine n pi over n. So if I take L'Hopital's rule, this gives me limit as n goes to infinity of, let's see, the derivative of the top. Derivative of cosine is negative sine times the derivative of the inside. So our variable is n. So then the derivative of the inside is just going to be pi over the denominator. So the derivative of n would give me 1. So I'd have negative sine of n pi times pi. So think about this. What's going to be inside here? N times pi. That's going to be like 1 pi, 2 pi, 3 pi, 4 pi. Well, taking sine of all of these is going to give us 0. So we'll always have negative 0 times pi, which is 0. So this is always going to be 0 over 1. So this is just 0. So that's one way to think about it. That's using L'Hopital's rule, which is very strong and it's often like a fix-all for us. Another way of doing this is by utilizing something we learned in 151 called the squeeze theorem. And so the squeeze theorem tells me that if I have a function that is kind of squeezed in between two functions, and those two functions have the same limit, then the thing in the middle must also have the same limit. Here's what I mean. We know that cosine of n pi, right? The cosine function on its own is greater than or equal to negative 1 and less than or equal to positive 1, right? No matter what n is, it'll always be between these two. Now let's divide everything by n. Whoops. So now dividing everything by n, we now have the function that we started with. So we can tell that cosine of n pi is squeezed between negative 1 over n and positive 1 over n. Well, if I take the limit as n goes to infinity of negative 1 over n, so this is with a limit, limit as n goes to infinity of negative 1 over n would be 0. Then we'd get something in here, right? That's the thing we're trying to evaluate. And that has to be less than or equal to the limit as n goes to infinity of 1 over n, which is 0. And so since this has to be in between 0 and 0, we know that this is also going to be 0. So that's what the squeeze theorem tells us. It's squeezed in between two functions. The limit of both of those functions is 0. So then the limit of the function we started with has to be 0. So it's just two ways to look at how we get our answer here. Similarly, we can use the same thing right here. We can use a squeeze theorem, or we can just utilize this fact about sine of n pi. And so if I look at sine of n pi, that's always going to be 0, so we're always going to have 0 over n. So this is just going to be 0. Now let's look at how we determine the limit of alternating sequences. Right, so if we have sequences that are alternating signs between positive and negative, how do we figure out the limit of them? What we're going to say is that the limit as n goes to infinity of an alternating sequence only converges if the limit as n goes to infinity of the absolute value of that sequence is equal to 0. Okay, so here's what I mean. So we already know that this limit should be equal to 0, right? We've done it before. So actually, I'm really not sure why I put it in there. We can, so this is probably why I put it in there. If we look at a sub 1, this would be cosine of pi over n, so that'd be negative 1 over n. If I look at a sub 2, this would be cosine of 2 pi over n, so it'd be 1 over 2. A sub 3 would be negative 1 over 3. A sub 4 would be 1 over 4. So what we can say here is that the absolute value of these numbers over here, sorry, this should have been 1. The absolute value of these numbers over here is tending to 0. Right, and so that's another way for us to say that this the limit of this sequence is equal to 0. So we've now got 3 different things we can use there. We can use our definition for the limit of alternating sequences. We can use the squeeze theorem, or we could use L'Hopital's rule. So now let's look at example 19, where we actually have to look at an absolute value. So this is going to be, so we know since this is alternating, we know it's alternating since it has this negative 1 to the n. And so the limit of, as n goes to infinity of this alternating sequence, we need to take an absolute value. So now we need to think about what does the absolute value actually do to this function. Well, all it does is it forces that top to be positive. So that means we're always going to have 1 over 2n plus 2. And so now taking the limit of this, I see that we would get 1 over infinity, which would give us 0. Okay. Now let's look at example 20. So for example 20, we would have, let's see, a sub 1 would be 3 minus 0.4. A sub 2, we'd have 3 plus 0.16, because that's negative 0.4 squared, and then so on. So it doesn't look like this is actually going to be an alternating sequence, because here, even 3 minus 0.4, that's still a positive number. But here's how I want to look at this. If I was going to take the limit of this sequence, this is what we would get. Now, if I'm actually trying to take a limit here, I don't need to worry about the 3 because there's no n's there. So we can call this 3 plus the limit as n goes to infinity of negative 0.4 to the n. And so now we have an alternating sequence in this part right here. So now we're just going to look at the absolute value of it. So this is going to be 3 plus the limit as n goes to infinity. If I take an absolute value of this, then it's just going to be equal to 0.4 to the n. And as n goes to infinity, we can kind of think of this as, we can think of 0.4 as just 2 over 5. And so the denominator is going to be growing faster than the numerator, which means that the denominator is going to be getting infinitely bigger than the numerator. So we can say that this is going to be 3 plus 0, which is 3. Now, for example 21, I'm going to split this. So let's see. Let's first look at a sub n, right? So this is the limit as n goes to infinity of cosine of n. This one is not going to exist because cosine oscillates, right? And here, now, so if I had something that was like, say, n pi, or n plus pi over 2, that would be fine because our terms would always be equal to 0. But when it's something like just cosine of n, then this is going to be oscillating, so we can say that the limit does not exist due to oscillation. Now for b sub n, we're going to have limit as n goes to infinity of cosine of 1 over n. So what I'm going to do here is I'm going to move that limit inside of our cosine function. So we're going to have cosine of limit as n goes to infinity of 1 over n. The limit as n goes to infinity of 1 over n is 0, so this is just going to be cosine of 0, which is 1. So here's an example of when we have a trig function and we just slightly change what's inside the parentheses, and that can change us from having a limit that doesn't exist to actually having a limit that we can figure out. All right. Example 22, I'm going to leave as a practice problem. All right, one way you can do this is by squeeze theorem. And then, let's see, thinking about a different way to do it. Actually, I would go with squeeze theorem here. I think that's going to be the best bet. The other thing to think about is what is happening in the numerator. What are our values between? And what's going on in the denominator. But that's going to be very similar to us just using squeeze theorem. Okay. Now, as always, these lecture videos are both fun and exciting, so I need to provide some definitions that are both fun and exciting. We're going to say that a sequence is increasing. This should say is increasing if a sub n plus 1 is greater than a sub n for all n greater than or equal to 1. So an example of something like this is 1 is less than 2 is less than 3, right? My terms just keep on getting bigger every time. And so if they're always getting bigger from one term to the next for every term in the sequence, then we say it's an increasing series. We say that it's decreasing if a sub n plus 1 is less than a sub n for all n greater than or equal to 1. An example of this would be 0 is greater than negative 1, which is greater than negative 2, which is greater than so on, right? Every time I move to my successor is less than the term I started at, right? So if I go to 0 to negative 1 is greater than 0. If I go from negative 1 to negative 2 is greater than negative 1. If a sequence is increasing or decreasing, then we call it monotonic. Right, so these definitions in here are going to be very key to understanding things from here on out. So these are definitely things we need to start getting down. We say that a sequence is bounded above if there's a number m such that a sub n is less than or equal to m for all n greater than or equal to 1. What this means is that I can pick some number, right? Let's say I pick the number 10, and every term in my sequence is less than or equal to 10. That would mean that 10 is an upper bound for our sequence. Similarly, we say that it's bounded below if there's a number lowercase m such that a sub n is greater than or equal to m for all n greater than or equal to 1. Right? So I could pick something like, say, negative 2. If every term in my sequence is greater than or equal to negative 2, then I say that my sequence has a lower bound. Now, a sequence is bounded if it has an upper bound and a lower bound, right? Meaning it's bounded above and below. So we pick two numbers, and all of the terms in our sequence fall in between those two numbers. And then here's the reason why we're developing all that stuff. The monotonic sequence theorem says that every bounded monotonic sequence is convergence. So that means if we have an upper bound, a lower bound, and our sequence is only increasing or only decreasing, then we automatically know that our sequence is convergent. So let's look at example 23, see if we can use this. We're given a sub n equals 3 over n plus 5. So what I notice here is that as n is increasing, the denominator is just getting bigger and bigger every single time. And so, like we've discussed before, if our denominator is getting bigger, that means that the fraction itself is getting smaller. So I can say that a sub n, different color, a sub n is decreasing, right? That tells me it's monotonic. I can also say that every term is going to be less than or equal to 3. A sub n is less than or equal to 3 for all n. Greater than or equal to 1. Right? Because if I plug in 1, that's the smallest that our denominator is going to be, which means that's the biggest this fraction is going to be. And plugging in 1, we'd get 3 over 6. So that means our terms are never going to get bigger than 3 over 6. So they'll certainly be less than or equal to 3. So now I have an upper bound. Well, I can also say that this denominator and this numerator is never going to be negative. So I can also say that negative 1 is less than or equal to a sub n for all n greater than or equal to 1. Notice I'm not being precise here. I'm not getting as close as I can to the sequence. I'm just trying to find an upper bound, a lower bound, and if it's monotonic. Since I've done those three things, it's monotonic, it has an upper bound, it has a lower bound. That tells me by the monotonic sequence theorem, it converges. And then if we take the limit as n goes to infinity of the sequence a sub n, we will be tending towards 3 over infinity, which will give us 0. Right? So it actually, we could have been a little bit more precise on our lower bound by saying that our lower bound is 0. But we don't need to, when we're just talking about a lower bound, we don't need to be just, as precise as possible. Okay. Now we're looking at a sequence given by e to the negative n. The first thing I want to note is that e is approximately equal to 2.7. Okay, so what we're really looking at is 2.7 to the negative n. So this is 1 over 2.7 to the n. So again, our denominator is just going to be getting bigger and bigger and bigger, making this fraction smaller and smaller and smaller. So I'm going to say that we have an upper bound of 1. Our numerator and denominator will never be negative, so I have a lower bound of negative 1. And I know that this is going to be decreasing, which means it's monotonic. So then by the monotonic sequence theorem, we get that this converges. Okay, and so now we want to find the limit as n goes to infinity of this guy. So again, our denominator is staying constant, and our our numerator staying constant and our denominator is getting infinitely big. So this is going to be going to 0. Now let's look at example 25. Alright, so I know, let's just look at these terms. This is going to be like a sub 1 equals 2.7, or is approximately equal to 2.7 to the 1 over 1. So this is just 2.7. A sub 2 is approximately equal to 2.7 squared over 2. Okay, so we need to think about, did this get bigger? Well, we multiplied 2.7 by itself and then divided by 2. So I divided by a number that was smaller than what I was multiplying by. So that means that this did get bigger. Now let's look at a sub 3. So this would be 2.7 cubed over 3. And so now I want to think about, okay, well, what's happening here? 2.7 cubed, that's going to be somewhere in between 8 and 27. Right, so it lies somewhere in here. And then we'll divide by 3. Right, because I have a divided by 3 right here. I know that a sub 2 lies somewhere in between, so let's see. This would be 4 over 2 and 9 over 2. Right, so it's lying somewhere in between 2 and 4.5. This one's 2 point, let's see. That would be 2.6 repeating and 9. So the goal is to figure out, okay, did A3 get bigger than A2? Well, this isn't giving me much, right? Because let's say A2 was something like 4, but A3 was 3, then that would say that this is decreasing from A2 to A3. So that method isn't going to work. So instead, what I'm going to do is I'm going to look at, what did I multiply my numerator by? So on top, I multiplied by 2.7. On bottom, I must have multiplied by 3 over 2. So again, the number I'm multiplying by on top is bigger, which tells me that I'm multiplying by something greater than 1, so this has to be increasing. And in fact, this is going to be increasing the rest of the time. So we've discovered that this is an increasing sequence. Now, what I want to know is, do we have an upper bound or lower bound? Well, we certainly have a lower bound of 2, since this is increasing the entire time. This must be our smallest term. So I could even say that we have a lower bound of 2.7, but just to be safe, we'll say 2. Okay, now I need to look at what is actually happening here, right? How fast is this numerator growing? How fast is this denominator growing? So we need to look at, what does e to the n look like? Well, e to the n looks something like, let's see. I believe it looks something like, something like this. Whereas, let me get a better graph. Alright, e to the n, so should have like 1. It'll be at 2.7. Alright. Alright, so this is my e to the n graph. This will be my just n graph, right? This is just a straight line. And so we need to notice that this black curve is growing a lot faster than the maroon curve, which tells me that the numerator is growing much faster than the denominator. So this is going to get infinitely big. So we can say that we have no upper bound. And so what we've just figured out from doing this is that since it has no upper bound and it's increasing forever, it must diverge to infinity. Because if it converged to something, say it converged to like 200, then we could have an upper bound of 205. Now let's look at, and I guess another like mathematical way of looking at that, we could have taken our limit as n goes to infinity of e to the n over n. If we take L'Hopital's rule of that, then this would give us e to the n over 1. Right, sorry. This would give us the limit as n goes to infinity of e to the n over 1. So we'd get infinity. Now let's look at example 26. So for this one, I'd like to notice that a1 is equal to, let's see, this would be 1 times pi over 2. So that would be 0. a2, that'd be 2 pi over 2, so that'd just be pi. So that'd be cosine of pi, which is negative 1. a3, that would be 3 pi over 2. So cosine of 3 pi over 2 will give us 0. Then we'll get a4 is 4 pi over 2, so that's 2 pi. Cosine of 2 pi gives us positive 1. And it's just going to proceed with this pattern on and on forever. So although we have an upper bound and a lower bound here, using 1 and negative 1, it is non-monotonic. Since this is non-monotonic, we know that it's going to, so a couple different things. One, it's non-monotonic. And we're kind of actually, if we look at A2, A4, A6, A8, and onwards, we're going to be oscillating between 1 and negative 1. Okay, so we could look at the absolute value of a sequence like this, and we're not going to get that the absolute value goes to 0. So this tells us that our sequence diverges. For example 27, I'd like you to look at what the first few terms are and then see if you can get this one. So I'm going to leave this as a practice problem. Now looking at example 28, I want to look at, so let's see, A1 is 2. A2, that would be 1 minus 1 over 2. So that gives us, that gives us 1/2. A3, that's going to be 1 minus 1 over 1/2. So that's 1 minus 2, which is negative 1. And then A4 would be 1 minus 1 over negative 1. So that's 1 plus 1, which is 2. And now I have a thought here, which is that we've wrapped back around to A1. But let's see. So A5, this would be 1 minus 1 over 2, which is 1/2. And so we have. Because notice here that this is a recursive sequence, so every term is built on the previous term. So if I get back to 2 here, which we did for a sub 4, then we're just going to repeat this cycle over and over again, which tells me that yes, we have an upper bound of 2, we have a lower bound of negative 1, but this is non-monotonic, and so we say it diverges, because its absolute value is not approaching 0. Alright. for example 29, this is the tough one. And it's not incredibly tough in terms of defining if it, finding out if it converges or diverges, but it is pretty tough to figure out what it converges / diverges to. So because of that, what I want to do is I just want to look at what happens for our convergence. So I'm going to tell you that it converges. I want you to practice figuring that out. Right? So if we're determining it converges, we can probably use our monotonic sequence theorem. So go ahead and see if you can use that. And now I want to see, okay, what does it converge to? So if I'm telling you it converges, that means the limit as n goes to infinity of a sub n is equal to L. So that means that, so let's see. We were given a sub 1 equals 4, a sub n plus 1 is equal to 12 over 8 minus a sub n. Alright, so then the limit as n goes to infinity of a sub n plus 1, well, keep in mind this is going to be using our a sub n plus 1 formula right here. So this is going to be 12 over 8 minus a sub n. Now, if I move this limit inside of our fraction, we're going to get 12 divided by 8 minus the limit as n goes to infinity of a sub n. And so this will give me 12 over 8 minus L. Now here's the key thing. The limit of these sequences has to be the same, because the a sub n sequence, right, that'll be the same as the a sub n plus 1 sequence, except for it includes one extra term at the beginning. So we know that L has to be equal to 12 over 8 minus L. Multiplying across, this will give me 8L minus L squared is equal to 12. So 8L minus L squared minus 12 is equal to 0. Factoring this, we'll get L minus 6 times L minus 2 is equal to 0. So L equals 6 or L equals 2. What's going to be key here is that you will figure out in the top part that we can get an upper bound of 4 and a lower bound of 0. So that means that this cannot be the limit because it does not lie within those bounds. So then our limit is going to be L equals 2. And if you calculate A1, A2, A3, A4, A5, you should be able to see that pretty closely in what those fractions are. Alright, that'll wrap it up for this section. I hope y'all had a great and exciting time as always, because math is just such a joyride. And I will see y'all next week.